Okay, this is more than a little bit out of order, but in this chapter, I'm going to start with equation 19.14, and this should be associated with the question of what makes magnets work, how relativity makes magnets work, which is a video by Veritasium, and I just wanted to kind of go through some of the math that might get you from what the concepts that they give you in this video to how you would get to equation 19.14 right here. So what I'm going to start with is a discussion of a wire carrying current. So when the wire is carrying current, basically the positive charge are stationary and the negative charges are moving, and the whole thing is neutral. The whole wire is neutral. So in the reference frame where the wire is sitting still, there's this wire, and if you put another wire next to it, plus, 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 it will also be neutral. And so one would not expect any kind of electric field between them. But we would have a magnetic field, and the magnetic fields will cause the wires to be pulled together, and the actual value of that is force divided by length is mu sub naught times the current in the first wire times the current in the second wire divided by 2 pi d, the distance between the two wires. And this was actually pretty much the equation that defined what the amp was and what the coulomb was, because they determined mu sub naught was some, I think is 4 pi times 10 to the negative 7th. And the reason it's 4 pi times 10 to the negative 7th was because 4 pi divided by 2 pi is 2, and it just is 2 times 10 to the negative 7th times I1 times I2 divided by d. So that is an equation that just came from an experiment. And that was the experiment that defined the ampere, and it also defined the coulomb. It just happened to be that they were using, for force, they were using dynes, which is kind of, I forget exactly what a dyne is. It's like 10 to the negative 5th, 10 to the negative 5th newtons, I think. And for the length, they were using centimeters, I think. So they ended up with a 10 to the negative 7th in there. So to start this kind of an analysis of this thing, let's remind ourselves that the current is the amount of charge passing a point in the wire divided by time. And the current would be the density of charge times the volume divided by delta t. I'm going to express the density, we'll call that volume the cross-sectional area times the delta x over delta t. And then we will go ahead and say that the density, okay, this seems like I already had delta Q over there, but the density is also the charge divided by the volume. So, okay, so this is kind of weird. It looks like I'm going backwards. Then that can be separated into Q over delta X. Wait. Yeah, we're gonna call that Q over delta X times A delta X. Okay, so A cancels out, and we're going to change the name of Q over delta X to the linear charge density, which I'm going to call lambda sub Q. And then we'll have lambda sub q delta x. And I forgot to put the delta t under each of these, so delta x, delta t, and delta x, delta t. So finally, we'll have this is the linear charge density times this delta x, delta t is going to be called the drift velocity of the particles. So now we've got a fairly simple expression for the current in terms of two relevant things, the linear charge density and the drift velocity. Now let's say I hop over to one of these electrons that is moving at the drift velocity in this direction. What happens then is that the positive charges, their linear density increases, which means they bunch up together in my frame of reference. On the other hand, the electrons around me, their linear density decreases. And because they were Lorentz contracted in the original frame, now they become uncontracted now that I am moving along with them. Same thing up here. The linear density of the protons increases, and the linear density of the electrons decreases. Okay, let me talk about a couple of directions that I kind of want to go. And one of them seems wrong because it's giving me the wrong result, and the other one might give me the right result. The first thought I have is putting these two wires together and considering that in both of them, from the perspective of a particle traveling at the drift velocity, the the linear density of the protons here increases, the linear density of the electrons decreases, giving us a net positive charge. The linear density of the protons here goes positive, and the linear density of the electrons goes negative there, which also gives us a net positive charge, which would result in a repellent situation. So I'm a little at a loss there because they should be attractive if the current is going the same direction in both wires. However, if we ignore and just say, okay, don't worry about the rest of the wire, just worry about me, the electron, which is another thing you can do, of course, because this. Okay, let's just say I'm an electron. If the linear density of the protons there goes up and the linear density of the electrons goes down, then just as that electron, yes, I am feeling an attractive force to that wire. So I'm not quite sure right now how to resolve that. Maybe I'll add that at a later time. But let's just go with that. Let's just go with just a single electron, which means I'm no longer going to be trying to derive equation 19.4, but instead I will be combining force equals qv cross b with b equals mu sub naught I over 2 pi r. So let's see if we can derive force equals qv times b, and b is mu sub naught I over 2 pi r. All right. Also, this v is no longer the drift velocity. V is going to be associated with the current, but not the drift velocity. Let's see what else I can do here. I can replace I with lambda sub q v sub d, and that goes up here. Or, I'm sorry, lambda sub q v sub d. And lambda sub q, what is that going to be? Is it going to be, are these additive? The charge density of the protons minus the charge density of the electrons? So yeah, let's come back to Gauss' law for electric fields, which says that basically phi equals electric field times the area equals the charge enclosed divided by epsilon naught. Here we've got a wire enclosed by a cylinder, so the charge enclosed is going to be lambda of the protons minus lambda of the electrons times d, and then the area enclosed over epsilon naught equals the electric field times the area, which is 2 pi r times d. And so we will get the electric field equals, dividing out things, and we have this equation here. The electric field is lambda p minus lambda e over 2 pi r epsilon naught. Okay. Now, lambda p is the original charge density, charge carrier density, times cosh phi, and lambda e is going to go down, so it is the original charge density time divided by cosh phi. And phi here is phi is arctange of v over c. Okay, and this is all divided by 2 pi r. And let's also note that c is the square root of mu sub naught times epsilon naught. I think that's right. Or is it 1 over? 1 over square root of mu sub naught epsilon naught. So epsilon naught, did I write that right? Okay, it can be replaced with 1 over mu sub naught c squared. So I'm going to put mu sub naught c squared up here at the top. And that simplifies to lambda mu sub naught c squared over 2 pi r times, and I just multiply by cosh phi over cosh phi, and I end up with cosh squared phi minus 1 over cosh phi, which is sinh phi over cosh phi, which is tanh phi, which is tanh phi is v over c. So, all right, equals. So lambda mu sub naught vc over 2 pi r. Whoa, where did my drift velocity go? Somewhere. Where did my drift velocity go? Actually, I don't think it's the drift velocity that I'm missing. It's actually the velocity of the particle that I'm missing. And the reason that's missing is because I made a mistake. It's because what I did here, that I said the lambda sub p minus lambda sub e, and then associated that with. And when I introduced phi, here is where I think what I did there was I put the drift velocity into that equation. So this is phi drift, the rapidity of the drift velocity. And what I did is very much like what Veritasium did in his video, because he also only considered a particle moving at the drift velocity. Actually, no, he was thinking about 2 wires going in the same, with the same current. So yeah, let's come back to that, because if I go ahead and use 2 wires with the same current in them, I'll have an excuse to use the same drift velocity. Yeah, because then I can make the claim that the velocity of the electron is the same as the drift velocity of the other wire. Okay, and now let's come back to that weird question that I asked about the positive charges and the negative charges, and what I am going to say is a point that I have made in another video, um, and it is something that I call the principle of force feeling. And this is an argument that I was making related to some technical argument of general relativity, where um, where somebody tried to use some strange math to calculate the amount of force that was on distant uh, particles in the universe. And I suggested that instead, it was, what were they, what was it they were doing? Okay, well, I made a 20-minute video on it um, on YouTube. It's called The Principle of Force Feeling, Cosmology and Newton's Shells. And basically my argument in The Principle of Force Feeling was that if you are trying to calculate the amount of force on an object in a situation where for some reason maybe infinite sums apply, then what you should do is start from its perspective. Like, if I started from this guy's perspective and looked around him, then everybody around him is pulling to the right on this point. And he would say, well, most of the things I see is pulling to the right on that guy, so it should pull my direction. Well, I did not agree with that sentiment. I said that you should start and look at the terms that are nearest and most dominant first. To calculate the force on something, you should try to look at the universe through its perspective. Now, so that is what I'm going to apply here to this situation. Why would the positive charges not be attracted to the other wire? Because you should look at the situation from the perspective of the positive charges. And the positive charges are not feeling a net force towards that neutral wire, because from its perspective, the linear density of the electrons and the linear density of the protons are equal. But from the perspective of the electrons moving at the drift velocity, the proton density has gone up, the electron density has gone down, and so you will have a net force towards the other wire. Okay, so where am I at? I have derived this. Electric field equals lambda mu sub naught v c over 2 pi r. And what I would like to derive is force over length is mu sub naught I1 I2 over 2 pi r. I'm not sure whether I'm going to get there or if I've made some kind of mistake, but I can replace the linear density times the velocity with, or the drift velocity, with the current in the second wire. Okay, and I corrected that. That should have been a mu sub naught there, not a v sub d. And then multiplying by the charge in the other wire, you get lambda 1L times, and then multiply by I2 mu sub naught c over 2 pi r. And then we'll divide by L. And divide by L, and I get mu sub naught I1, lambda sub 1, lambda 1 I2 mu sub naught c over 2 pi r. Good. And then it looks like we're off by a factor of v sub d over c. If we could find a reason to multiply by v sub d over c, we'd be there. And here it is. Cosh squared phi minus 1 over cosh phi is sinh squared phi over cosh phi, which is, so that should have been Vc sinh phi, right there. So we had tanh phi times sinh phi, which tanh phi would be V over C. Sinh phi for low velocities is very close to tanh phi. So instead of V sub D over C, we're going to have sinh of arctangh phi. And so there we go, which is so close to V sub D over C that that's going to get us there with a little bit of an approximation.